Next slide, please. Yeah, it happens fairly often. Somebody changed the batteries. So I didn't see, but how many people have not been, are not from Houston, Texas? Okay, so this is my opportunity to welcome you, and Space Center Houston to welcome you to Houston, Texas. This is a picture of Houston, Texas, taken from the space station 250 miles up. The space station is flying up there today. It is going 17,500 miles an hour around the surface of the Earth. And at that speed, you can go all the way around the Earth in 90 minutes, which is pretty hard to comprehend. That means 45 minutes of daytime on the day side, 45 minutes of nighttime, 16 times in a 24-hour day. But from the reality of taking the picture, if you were up there and you'd promised to take a picture of Houston, Texas for a friend, you got to remember that that speed means you're going about 5 miles per second over the ground. The space station is big. You could be in a module somewhere doing experiments. We're going 5 miles a second and you have to set your clock. You need to know where you are over the Earth so you can get from your laboratory or sleep module or wherever it is you are, pick up the cameras, check the lenses, get to the right window. Now, which window do you go to? Because it depends on which way the spacecraft is oriented. You could get to a window, but it's looking into deep space and you wouldn't see Houston. All that comes together, you take the lens cap off, and if you get there to the window 10 seconds late, that's 50 miles. Houston's gone. So, like all good NASA astronauts and crew and planners, your primary plan was to take a picture of Houston, but you also have a friend in New Orleans. So if you just hang out by the window, sooner or later they have a picture for somebody, and that'll be a big help. So here we go. I got into, this is another picture from space. I got into, my interest in NASA was started really with the Mercury program. I'm from Rocky River, Ohio, which is on the northern part of Ohio, west of Cleveland. And this is a picture of the Great Lakes. What looks odd about that? Well, it doesn't look like it does in the geography books. I know that because NASA has special geography books, because in school geography books, north is at the top of the picture. In NASA geography books, doesn't have to be. Depends on which way the spacecraft's going, what's the orientation of the vehicle. Just happened to be, that's what it looked like out the window when somebody took a picture. North is actually on the right side. And let me see if I can operate this. That's Lake Erie, Cleveland's about there, Rocky River's over there. It's not too far from what's now the Glenn Research Center. And I was very interested in the space program early on because everyone was excited by Sputnik, by Yuri Gagarin, and the whole possibility of flying in space. And to me, the possibility of flying in space was really exciting. Seemed like a cool job, and I really wanted to do it. I mean, but at the same time, I was watching Superman leap off, faster than a speeding bullet, more powerful than a locomotive, and able to leap tall buildings with a single bound. So flying in space just seemed like another one of those cool things to do. I was very fortunate. So the fortunate part was my parents encouraged my curiosity. The schools had changed a lot with, I think, the beginning of the Sputnik and Gagarin and all the rest of that. So in school, I was studying very early on how things work, how to take them apart, put them back together. That was sort of unsupervised or at home. At the same time, I studied Latin for a little while in school and then French. So that sort of fell into that whole thing that the president said about do things that are hard. Don't do things that are easy, do things that are hard because they're hard. And it turned out that studying Latin made English easier for me, and it made French a lot easier, and later on it made Russian easier. This story is about how we made a team with the Russians to build a space station that we now had. So next slide, went from Cleveland to, now this one is, at least north is at the top of the picture, so this is an easy one. Anyone recognize where this is? Massachusetts, absolutely right. And you can see there's Long Island, Cape Cod, and Cape Cod sort of points back at Boston and Cambridge. That's where MIT is. That was sort of, by then I was in college and I was really thinking about engineering. I'd been a pilot for a while. And this is really sort of where flying in space began to come into focus. It was a little bit more than just a dream of a 12-year-old. It was now getting to be a possibility, and that led to test pilot school and ultimately to flying in space. I did fly on 3 missions, as you heard, and the one I want to talk about today is this one, represented by this patch here, which shows our concept of the crew that designs these patches. So what the patch shows is Atlantis on the bottom with the arm, which we carried a docking module made in Russia, and we attached it to the airlock in the back of Atlantis, and then flew Atlantis so we could attach the top to this thing hanging down from the Russian space station Mir. And that was our primary mission, which was to build a bridge between NASA and the US space program and Mir and the Russian space program. And we hadn't done that or hadn't done anything quite like that since 1975 or 76. And there had been a lot of Cold War passing during all that time. So when it came time to get ready to do that, NASA looked around. I had flown once as a pilot and once as a commander. And while I was at MIT, for reasons that, again, seemed hard, but maybe that was the right thing to do, I studied Russian for 2 years while I was getting my degree. And the Marine Corps didn't need Russian, they sent me to Japan, but NASA did. And I was selected to go there and study with them, work with them, and then command the mission. And you can see the flags at the bottom of this patch, US, Canada, and Russia. What's not shown is that one of the Russian crew members was actually from the European Space Agency. But when we did this, I was the only guy on Atlantis that could speak any Russian. And there was only one guy on here that could speak any English. So it made it extra sporty, I guess I would call it, challenging. On the ground, they had a lot of interpreters. Up where we were, not so much. So we get most of this is a picture most everybody will recognize. Again, north is at the top of the picture. And this is where MIT and Rocky River and all the NASA led to. This is where the astronauts go. This is where we think the space starts. Johnson Space Center is engineering, training, families go here, kids go to school, but the hardware is down there. We really like going down to see it. And to orient yourself, for those of you who have kids, you will recognize this part of the center of Florida, near Orlando, as the center of the known universe. Really big mice live there, along with everybody else. But if you want to go to space, you go about 50 miles to the east, and that's where Kennedy Space Center is located. That's where the launch pad is. And let me remind you that that launch pad in Florida is on a planet that's rotating around its north-south pole axis one time all the way around in every 24 hours. Which means, since the planet is 8,000 miles in diameter, that the launch site right there is actually going to the east at almost 1,000 miles an hour. And by the way, so are you, and so am I, and so is this building. The whole Earth is rotating so that we're all kind of going to the east. I don't want to spoil anybody's plans to see a sunrise or a sunset, but think carefully about what you're looking at, because the sun is not rising, it's not setting. But have a glass of wine or an adult beverage of some kind in any case, because it is beautiful. So here we are on the pad. We're getting ready to launch, and we timed our launch so that the launch pad on a rotating planet would be in the plane of the orbit of the orbiting space station. Otherwise, we could launch, get to the right altitude, but if we weren't in the same orbital plane, we could never really dock, or we couldn't even rendezvous. We would not be able to do the mission right. So the launch is where it's going to take us up here to the Russian space station. This is the Mir as we saw it at the time, and right up here, this is a cruciform part. There's one long module that has 4 radial modules. One is sticking right out of the page at you, and that's where we're going to attach the top end of that docking module if everything worked according to plan. Going out to the launch pad on launch morning, we take a bus or a minivan out to the pad, go up the elevator, into the white room, which is here, inside the white room, and then down into the vehicle. And finally, on a launch count that starts about on a Monday for a Thursday launch. It's a 4-day process. When we get ready to go, we're on our backs in the vehicle. In the last 30 seconds of that 4-day process, the computers on board the shuttle actually launch the vehicle themselves. First, the last thing that happens, 6 seconds before we start the main engine. You can see the engines being steered, and then the computer fires the motors, release the boosters from the pad, and ignite the boosters at the same time. The whole program means we're opening around the wrong axis to align ourselves with that plane. We're chasing the station even now. And it's a rough ride. It's noisy. It's noisy to be there. It's noisy inside there. You're wearing a helmet, ear, all that. But we're going to have a rough ride for about 2 minutes because the boosters are releasing so much energy so quickly that there's a lot of turbulent flow, low frequency, very high amplitude noise or vibration. Once the boosters have quit, we drop them into the ocean about 30 miles out to sea. The vehicle continues powered by the fuel in the tank for another 6.5 minutes. And so in a total of 8.5 minutes, we've gone from the pad on a rotating planet to orbiting that planet at 17,500 miles an hour. It's pretty quiet now, and as soon as the engine quits, it gets real light in the cockpit because now we're in free fall. And when we look out the window, what do we see? Another geography quiz. North is not at the picture. What are we looking at? Gibraltar. Okay, remember, NASA starts with a plan, and then they make a backup plan in case something goes wrong with the plan. If during that 8.5 minutes of launch, something had happened, or something to the launch, the propulsion system, or to something else that made it not a good idea to go to orbit that day, we would need to have a backup plan. Where do we go? Well, it turns out that over here in Spain, on the left-hand side, we actually have 2 runways that are prepared for a shuttle to land. And down here in Morocco, we have 1 runway. And every time we launch a space shuttle, there's an astronaut and an entire crew over there at an abort landing site, ready to take the orbiter. If they can't make it to orbit, they're going to land across the Atlantic. And by the way, it's only 25 minutes from launch from Florida to being on the ground in Spain or Morocco. So you don't think that Virgin Galactic and all these other big airlines are thinking about this? It's unfortunately the ticket prices. If you have to ask, you probably can't afford it. So we're going to pass we don't need that place. We're going to keep on going. I get out of the orange flight suit that you saw us on the main picture, and the first thing I want to do is relax with a good book, right? What do you think the title of this book is? How to Fly the Space Shuttle, and I'm on page 3. It's actually our flight plan. All of the training that we've gone through for almost a year, working with a crew of 5 in the vehicle, the crew of 250 in mission control, all the other players, is to prepare us to devise a plan step by step that can get us to a Russian space station. And then, for every step that we have to take, we need to think, what happens if that step didn't work? What's our backup plan? So we wind up building a whole series of plans because it's not the plan that really counts. It's the act of planning that prepares you for what you are not sure is going to happen, but could. Everyone know who Murphy is? The guy who wrote the law, Murphy's Law? Right. If anything can go wrong, sooner or later it probably will. And if you butter your toast in the morning and drop it, you know which side's going to land down, most likely. So we have that in the space program, Murphy's Law, but we also have what I would call the law of unintended consequences, which means that no matter what happens going uphill or in any other part of the spacecraft, there's no situation that's so bad that you can't make it worse if you do the wrong thing. So you got to know what's going on. You got to know what's broken before you decide to make a fix. This simple thing, because imagine going to the dentist's office to get a tooth fixed, and the dentist is confused about which tooth has got the problem. You're going to wind up with one less tooth or one extra filling. It's hard to tell, but this is what we're really trained to avoid. So we get into the plan, then the first step is we use the robot arm to assemble the docking module, which was carried in the payload bay. This is an IMAX movie film slide. The camera is at the back of the payload bay. We're looking straight forward. The half circle there is the aft end of the crew module. And Chris has put it into position, then he relaxes the arm. The docking module is actually connected by a mechanical action, just like closing the door of a car. You gotta have some momentum so that the mechanism can get out of the way and then latch. That's the way cars do, that's the way trains do. And so he relaxed the arm, I fired thrusters, we bumped in. NASA doesn't use the word bumping, but or colliding, that's completely off. But energetic momentum transfer. Now that sounds like a NASA guy, right? We're gonna do that. We do it while we're upside down. Any ideas why that is? Just because we can? No, it's because, actually it's not because it's cool, it's because it's warm. The sun is shining on the Earth, the clouds reflect a lot of solar radiation up into the payload bay, and the mechanisms that we use to do this kind of thing don't behave nearly as well if they are as cold as deep space. So we want to warm the payload bay. Again, this is learned over a lot of lessons, this is part of the plan, and this is the way we do it. So then, we fly up, we're continuing, all while we're doing this, we're chasing the Russian space station until we get up close. Now Chris has moved the robot arm out of the way, and there's a camera right here on the elbow, which is looking right at the top of the docking module, because I can't see it. From the position I am, this is like having a big chimney sticking up out of the payload bay, and I can't see to do the docking precisely unless I look at a camera that shows my closure and another one that shows how I'm lined up left and right. And this comes to one of the key things about building a team, especially a team of people from other nations and perhaps nations who are not our friends necessarily beforehand, is you have to build trust. And the way you build trust is two things. You demonstrate capabilities, and then you demonstrate that you will do exactly what you said you were going to do when you said you were going to do it. And that's sort of a key thing for trust, is if the other side can trust us or be confident that we will do what we said we were going to do when we said we would do it, and we expect the same of them. That's really how teams come together in business and in many other endeavors. So we had to dock Atlantis and this docking module to Mir right on time, right over Moscow, so they could get the data down while we were flying at 5 miles per second over the ground, which made it a very challenging orbital mechanics as well as a challenging flying task. And yet you have to remember that the space station Mir was designed to be flown up to by these little spacecraft like that one, which is the Soyuz. On the ground, that spacecraft weighs about 20,000 pounds. And it flies up and then docks, that energetic momentum transfer, sometimes called bumping, to the space station. That was designed for them. Our space shuttle on the ground weighs about 240,000 pounds, almost a quarter of a million pounds, but I would say about 12 times more massive than the Soyuz. So we need to be 12 times more careful, at least, so that we don't damage their space station when we're docking. Because the fundamental principle that I laid out when I went there to work with the Russians, see what they were doing, learn who they were, show them who we were, is when you're going to do something like this, you got to have some guiding ideas. My guiding idea was, don't break the other guy's spaceship. That's just going to take all the fun out of flying together and ruin the whole team concept. So we had to be very careful not to damage. When we came up there in this big giant spacecraft, which was piloted from the Russians' point of view by 5 cowboys. They knew we knew what we were doing, but still, this is their only spaceship, and we needed to make sure we didn't break it. We didn't, and once we got inside, you can see that I'm shaking hands with the commander of the Russian space station Mir. His name is Yuri Gidzenko. He used to be a MiG-23 fighter pilot back in the bad old days, when he was based in what used to be called East Germany, with the nose of his aircraft pointed to the west. And many of our astronauts were in the US Air Force, with their noses, based in West Germany at the time, pointed to the east. And so this was a part of the question was, how are we going to get along together? How are we going to work together since we were, sort of the opposing military forces? In fact, I studied Russian at MIT because I wanted to know more about these big airplanes, just in case I ever had to see one, in a real situation. Well, I can tell you that the Russian pilots are a lot like the American pilots, and they are focused on accomplishing their mission, taking care of their vehicle and their crew just the same way we are. We think alike. I think we're in many ways wired the same way. It's just a matter of, where they train, where they live, what they were raised to do, and how they were raised to do it. So we were quite confident of each other, and we're still correspond and are friends, even given the situation today. So another way that we wanted to build this team was recognize that this is human spaceflight, people flying around up there. And one way to get to know people a little better outside of work is to go out and have dinner together. Do something together that's sort of relaxing, that everybody's going to want to do. And so we planned in advance to invite the Russian crew of Mir, the crew of Mir, Russian and German, over to Atlantis to have dinner together. It was dessert. And then this opportunity came about a couple of months before launch when they explained to me that aside from focusing on the docking and doing that right on time, what we promised we would do, not break their spacecraft, all the usual, what I considered priority one things. They mentioned that the Russians were actually up there with the German to gather medical data for doctors in Russia and Europe on how the body changes over time exposed to weightlessness in the space environment. And when doctors are involved in an experiment like that, the cosmonauts are going to see needles, and they're going to be collecting blood specimens a couple of times a day and freezing them every day. Urine specimens a couple of times a day, freezing them, and saliva specimens. All those specimens, if they can get it back to Earth and thaw them out and process them, they will see the chemistry of the human body as it changes over time from day 1 or 0 all the way up to day 90. So that was a new problem, but I saw it as a new opportunity because we had a NASA freezer, but just the one. And so when I raised this question at the big conference meeting before the launch, what happens if we get the Russian and ESA data and put it in the freezer? What happens if we have a problem with our freezer? And I just sort of let the question hang there. You got to be careful when you do this, but this was not my first rodeo, as they say. Nobody likes to have a question dropped on their desk right in front of everybody without having a solution as well, because we only had the one freezer. And the doctors, German, Russian, or everybody else, they were getting kind of concerned about this, because to them, this was all about the medical data, not about all this docking and spacecraft stuff. So I let that go for a couple of beats in the meeting, and then I said, well, the crew of Atlantis are all engineers. We're trained as pilots, but we understand the engineering of a freezer, and we know that if we can pack the freezer with some kind of thermal capacitance mass, I made that word up right on the spot, and freeze it all down to minus 17 degrees, that it'll stay frozen no matter what. We won't even need electricity, because it's going to be a frozen rock until we open the door, take the stuff out, put the payload in, close it back up, and we'll get it back home. So we can make this work. Well, they liked that plan right then and there. I mean, you give them a problem and give them an answer. They were sort of under pressure. And as I was leaving, I said, well, the crew will go over to the crew quarters and we'll figure out some kind of plain vanilla thermal capacitance mass to pack in there. And maybe chocolate chip. And that's what we did. Because we were having this meal, and we'd sent the whole menu over to them, up to the State Department, and then the Russian State Department, Russian Space Agency. I told the NASA people, don't say anything about this ice cream to anyone. Because if it leaks out, and the Russians find out, and then along the way, NASA changes their mind, if they think we're going to deliver ice cream and we don't, what does that do to our team building? Did we do what we said we were going to do when we said we were going to do it? No. You have to manage your customers, your teammates' expectations. When we brought ice cream out of that freezer, that's what Chris Hadfield is opening up over there, by surprise, they were just as delighted as could be. They were stunned. I would say their socks were rolled down, but this is weightlessness. So But they would have given us, we had 9.5 pounds of ice cream in there, and it was full. They would have given us anything they had on the space station for the rest of that ice cream. And of course, that was our plan all along, was to leave it there, because they had 3 more months to go. So that's what we did. And they just, I mean, they're still our friends. We flew over, there's Cape Cod over to the right-hand side. And, but the real purpose of this photograph was right there. That's New York and Long Island, New York City, and the United Nations. And we're in the same orbital track that Sputnik was in, and Yuri Gagarin, because they're all at that same inclination. Taking pictures of the UN from Atlantis while docked to a former Soviet space station. We also had the opportunity to, remember I mentioned I was dreaming of flying back when I was 12 in Rocky River, Ohio. Well, that's pretty much the way Superman did it. It was faster than a speeding bullet, and at 17,500 miles an hour, I was faster than a speeding bullet. So we left there, left the bridge attached to the station, and more shuttles then could come and do more of that, living and working together in space, building a team from what we started. And then you can see the orange docking module in the lower part. That's the result. That's our space program for today and for the near future, I think, but it's not the end of the space program. The next step in the space program is this. We're going to go back to the moon. And this is a picture of Earth from an Apollo vehicle orbiting the surface of the moon. And we need to go back there, only do things differently, stay longer, build a base. And if you think about Apollo 11, everybody celebrates that in July. It's the first landing. I celebrate Apollo 12, which happened in November of the same year. And Apollo 12 was different than Apollo 11. Rather than just being asked to go to the Sea of Tranquility somewhere, these guys were specifically targeting so as to land their vehicle, which is up there, within walking distance of the Surveyor satellite, which had been landed on the moon 3 years before. It's about 200 meters, a little over 600 feet. Well, that's closer. When you land at Hobby or Intercontinental Airport, it's farther than that to get to baggage claims. So they had to land that closely, and the reason they had to do it was to demonstrate this precision landing capability, because if you want to build a base, you're going to need a spaceport. You're going to need to be able to land at your destination so people can get out, walk to where they're going, unload cargo, and do everything else. And that is where I think the next step is, and I hope that some of you in this room are going to be involved in that. I'm pretty sure it's not going to be me, but some of you who are students now, and of course the step after that is building that base and then getting ready to go to Mars. That concludes what I had to say about building teams to build ISS and other big structures. Are there any questions?